Today we're discussing what is energy. Energy is the ability to do work. It even has the same units as work. What that means is energy is measured in joules, just like work is. And you could say it's the ability to do work, or sometimes what we talked about in our last lesson on work was if work is done, energy is transferred from one object to another. So if I do work pushing a car, I actually give that car energy. If I do negative work, I'm removing energy from the car. So a little review of some previous work that we've done. If we're lifting an object, work is FAD cos theta. Here we're not talking about the net work. We're talking about the work that I did on this object, and lifting this box, let's say. If I'm lifting it at a constant speed or constant velocity, that means this force is actually equal to this force. Okay? So in this equation, what we're actually talking about is the applied force. How much work did I do on it? Assuming theta is 0, assuming that the displacement is kind of straight up, like this. So assuming that's true, we can get rid of the cos theta. Remember, cosine of 0 is just 1, so that goes away. In this case, again, the FA that we're talking about is the force that we're talking about is FA. Okay, so this is really FA. But in this case, if we're lifting it at a constant velocity, then FA is equal to FG, which is just mg. Remember, FG here is mg. What we end up with then is, instead of FA, we could just say mg. And assuming that d, or maybe delta d is better to talk about, is just the height, then what we end up with here is work is equal to the change in mg delta h, or work is equal to mg delta h. Remember that mg delta h is going to be something that we're going to see today as we go through our equations. Okay, so this was kind of a little review. Sometimes in some of our work questions you probably ran across something like this, but I want you to remember this little thing as we kind of carry on and do stuff today. There's 3 basic forms of energy. Okay, there's potential energy. That's energy that's stored in some way. So if you've got a battery, that's probably like a type of chemical energy. Usually most batteries are chemical. We've got some kind of chemical energy. We could have nuclear energy. Some people break nuclear out into its own thing, but nuclear energy, gravitational, elastic, all these energies are stored energies. The most common one, this is gravitational. So that's why you see the G right here. Gravitational potential energy is mgh. Maybe I'll just write that here. This is gravitational. Before we get into our next one, gravitational potential energy. Oh, it's a long thing to write. People often abbreviate this GPE, just in case you see that. Gravitational potential energy. We will discuss a little bit chemical, nuclear, elastic. We'll discuss some of those, but the only one we're going to deal with as an equation in grade 11 is gravitational potential energy. That's first type of energy, stored energy. Second one is kinetic energy. Kinetic energy is kind of like released energy. It's energy that's no longer stored. Generally speaking, that means it's the energy of motion. So for example, you could kind of picture if I have an elastic band in my hand and I stretch that elastic band and I'm holding it stretched, that's stored energy. I've given it some elastic potential energy. When I release that, the elastic probably goes flying through the air. It becomes energy of motion. Okay, so when it's stored, it's elastic in that case. When I release it, it becomes motion. That's the one that we're going to talk about, is this what we call bulk kinetic. That just means the actual object itself is moving. There's other types, though, of stored energy of motion. Sound, for example. We'll talk about this in the sound unit a bit more, but as I make a sound, the molecules between me and my microphone for an iPad, or if you were in the room with me, remember those days when we could be in the same room together, but anyways, if we're in the same room together and I'm making a sound, I'm just vibrating air molecules between us, and that's how the sound travels to you. Thermal is also just molecules moving. If you heat something up, that something's molecules move faster. Electric is just electricity. That's like electrons flowing through wires. Anyways, what we're going to talk about is bulk kinetic. Okay, so this bulk kinetic, we're just going to call it kinetic energy. The equation there is half mv squared. We'll see this a lot in the future. We're not going to focus on these two today, but there's their equations as an introduction. Our third form is kind of a form of nuclear, and here's where nuclear is sometimes broken out. Rest mass energy. This was kind of Einstein's, I don't know, big brainchild that he sort of, I don't know if he discovered it, but he certainly popularized it. Mass is a form of energy. This is sometimes just considered a form of potential energy. If something has mass, then it has energy, or it's made of energy. And so he came along with the most famous equation of them all, right? Einstein, E equals mc squared. The E that we're talking about is energy, the M is just the mass, and the C is the speed of light in a vacuum. So quick reminder from grade 10 science, hopefully you remember this. The speed of light does change if you go into different mediums. So the speed of light in water or glass or air, they're all slightly different. The speed of light in a vacuum, though, this is a rounded value, but it's basically this 3 times 10 to the 8 meters per second. And why is this equation true? Come back in grade 12, we might talk about it a little bit, but there's a whole lesson in that by itself. But for our purposes, we're just going to use this thing. Okay, so E equals mc squared. If you've ever wondered what this equation is talking about, this is what it's talking about. Let's try it. Let me describe to you what is going on here. Nuclear energy is energy stored in the nucleus of an atom. So if I have a nuclear fission is the breaking apart of atoms. Okay, so if you had, let's say you had 2 protons, you would actually have 2 neutrons as well, and then 2 electrons kind of circling around here. Something like this. Here's your kind of classic view of an atom. There's a terrible circle, but you kind of have something like this. If you could rip this thing apart so that you'd have like a proton with an electron. This is helium, if you know your periodic table. And if you could break it apart into something like this, this would become hydrogen. And there's one of the protons went into this one. And one of the electrons, you could say a second proton went over here. So this helium atom is breaking down into 2 different hydrogen atoms. Some stuff happens with the neutrons. Let's ignore that for now. But you could say that the mass changes a little bit. So this is fission. This is my quick little lesson on fission over here. What happens, though, is you've got this mass. So let's say you start off with in nuclear reactors, they usually have a big rod. And you start off with this rod of material, and it's 1 kilogram. And you do some nuclear reactions, some nuclear fission. And it releases a bunch of energy, and you have less leftover mass at the end. Something that you'll notice, though, is these masses are different. Okay, this mass and this mass. You might say, wait a second, where's the missing mass? Maybe you remember from some previous science, you'd say, wait a second, mass, there's conservation of mass, right? Whatever mass I start with, I should end with the same mass. Here we end with a different mass. The reason is because some of that mass has been converted into energy. How much energy? The missing mass, first of all, is called the mass defect. If we use E equals mc squared using this mass defect, that will tell us how much energy was produced. Oh yeah, so here I am writing over my words again. Let's get rid of my words. They're already on the screen there. The missing mass, or the mass defect, we're going to sub in right here. Okay, so we started with 1 kilogram. We're left over with 0.9. The missing mass is 0.1 kilograms. Okay, so we're going to sub that in here, 0.1 kilograms. Remember, C is just the speed of light, and don't forget to square it. I know as soon as we get this exponent here, sometimes people forget the other exponent. Don't forget that exponent. We gotta square that thing. We square the speed of light, we times 0.1, we get this giant number here. That is the amount of energy produced over here during this nuclear reaction. Remember, a gram is like a Smartie. If you pick up a pack of Smarties, and you dump some Smarties in your hand, imagine 100 Smarties, that's about 100 grams. That was this missing mass. Well, let's say here, that's this missing mass. That released this energy, and I don't know if you can kind of conceptualize how much energy this is, but you can conceptualize this is a big number. It releases a lot of energy. If we can release the energy stored in an atomic nucleus, then we are going to produce a lot of energy. That's why nuclear energy is so enticing to use. In Ontario, I think about half of our electricity is produced using nuclear energy. The mass defect then is the difference between the reactants and the products. So on the left-hand side over here, reactants. On the right-hand side, we got some products. And then the missing mass, or the mass defect, that's converted into energy. Okay, and that's how we use this E equals mc squared equation. Our total energy then, remember we said there's kind of three forms of energy, three broad forms of energy. There's kinetic, potential, and rest mass. The equations that we're going to see then, the total energy that any object has is made up of, here's kinetic, here's gravitational potential. We did discuss how there's other forms of potential, but for our purposes, we're just going to consider gravitational. And then we've got this rest mass energy here. Why do we often just consider the mechanical energy? The mechanical energy is just the first part, so over here. Why do we just consider mechanical energy? Why do we leave off this mc squared? Well, kind of like we saw in our last example, that mc squared is so big that it often makes these numbers look like, I don't know, like they're so small. It's kind of like if you had a mountain here and then you had a few grains of sand over here. Those guys are so small, so small compared to this guy that we just don't even really see them. So we'll often leave off the mechanical energy. When we talk in our next lesson with conservation of energy, we'll talk about why it's safe to do that. And I'll show you why. We'll discuss it again then. Some interesting notes here. Energy is measured in joules, just like work. Couple maybe common things. Energy is also measured in other units as well. One is kilowatt hours. If you ever see your electricity bill, or maybe your parents' electricity bill, your electricity bill is measured in kilowatt hours. 1 kilowatt hour is 3.6 million joules. Okay, that MJ means million joules. And M is actually for megajoules, but mega means million. That might be a conversion that you need in our textbook or on one of our worksheets. I forget. There's one question where they mention that. Also, calories. If you ever read food labels or anything like that, calories, this is a capital C calorie. There's a difference between lowercase c and uppercase c, just a quick reminder or note. But 1 capital C calorie is this many joules, okay? Just over 4,000 joules. It's quite a few joules, so every calorie that you eat is a lot of joules. Here's some terms that you should be familiar with. I'm not going to quiz you or test you specifically on them, but you should have an idea what those are. So some of them I mentioned here, some of them I didn't mention here, so you could look those up if you want. You should at least be familiar with those terms. And there's some fun homework for you guys. Enjoy.